This is Unit 9 on intercept and slope bias, and as part of this unit we will talk quite a bit about mediation and moderation. So we're going to be talking about test bias. What is test bias? First of all, note what bias is not. If I have a test and I give it to two groups, and one group scores higher on the test on average and the other group scores lower, that in and of itself is not bias. In other words, a mean test score difference between groups is not test bias. For example, if I have a test measuring, say, how well people speak French, and I give my test to one group of people in France and another group of people in the United States, I might find that the people in France score higher on my test, but that wouldn't mean that my test is biased. It could just be that my test is detecting an accurate, a real difference between the two groups. One group could be simply better at speaking French. So what exactly is bias? So to think about bias, we want to be understanding the idea that we use tests to try to predict things. If I give a score on a test, that test should be related to something. When we've been talking about validity, we talk about how tests should correlate with things that they're supposed to correlate with. They should be able to predict the things they're supposed to be able to predict. So test bias, we're going to be thinking in terms of validity and thinking in terms of a test trying to predict something. And we can talk about two types of bias that might occur. One is where the test might overpredict one group and underpredict another group, and we'll call that intercept bias. And in other situations where the test might accurately or fairly well predict one group and poorly predict another group. In other words, it would have good validity for one group and poor validity for another, and we'll call that slope bias. For example, one of the common examples that's often used in talking about bias is using something like a GRE or graduate record exam to predict, say, performance in graduate school. Maybe I'm using the GRE to predict students' grades or their grade point average in graduate school. And if I had two groups, maybe there was maybe I had two different cultural groups, and I found that one group scored higher on the GRE and the other group scored lower, that in and of itself would not mean I have a problem with test bias, because that would just be a mean difference. Now, that could be a problem that I want to address. It would certainly indicate there's some kind of unfairness going on, but it could be that one group actually is better prepared for graduate school and another group actually is less well prepared. So the test could be detecting a real difference. It would certainly be a difference we'd want to address and correct, but the problem in that case wouldn't actually be the validity of my test. Intercept bias would be the situation where if I gave the GRE to two different groups, and for one group the GRE overpredicted their grades, their performance in graduate school, and for the other group the GRE underpredicted how well they would do. That would be intercept bias. Slope bias would be if I gave my test to two different groups, say we gave the GRE to two different groups, and if for one group the GRE was fairly accurate in predicting their grades, and for the other group it was not very accurate. That would be a difference in validity between the two groups, and that would be slope bias. As we're talking about bias and tests, also note that these issues are broader than just talking about test validity. Sometimes questions of intercept bias and slope bias can have important research questions that we might want to address by looking at intercept and slope bias. For example, maybe I have a measure of a positive social interaction, a questionnaire that I give to people to measure how much they're having positive interactions with significant close interpersonal relationships with other people. And maybe I think that positive social interaction might be related to psychological adjustment, that people who have positive interactions with others might have higher psychological adjustment. But we could ask questions of, does this process work the same for people who, say, are partnered, that maybe they're married or cohabiting with a partner, versus people who are single that don't have partners? So we could give a measure of social interaction to people and see so intercept bias might be that for one group, the same level of social interaction might predict higher psychological adjustment, and for another group, the same level of social interaction predicts lower psychological adjustment. So that would be intercept bias, and that in this case is not really showing a problem with the test, but it would be an important, interesting research question to look at. Or we could have a situation where maybe for one group, the positive social interaction really strongly predicts their psychological adjustment, and for the other group, the positive social interaction doesn't so much predict their psychological adjustment, and that would be slope bias. Again, this would be a situation where this could be an interesting research question, maybe not so much an issue of whether my test is valid or not. So intercept and slope bias are two general ideas that can have broad utility in all kinds of research applications. So let's start by talking about intercept bias. To test for intercept bias, I'm simply going to run a multiple regression equation. That's the equation we have at the top of this page here. And in this equation, I'll have an outcome variable y and a predictor variable x1. And x1 is going to be my predictor. I'll call that the test variable, and I'll use that term throughout this unit. And simply that's the target variable that I'm testing. So if I want to understand, is the GRE valid in predicting grade point average, GRE would be my test variable. If I'm wanting to use social interaction to predict psychological adjustment, then social interaction is my test variable. So the test variable is a target variable. It's the variable that I'm testing or the one that I'm wanting to validate. The criterion variable is a thing that the test variable is supposed to be able to predict. So maybe social interaction is supposed to predict psychological adjustment. So psychological adjustment would be my criterion. Or if GRE is supposed to predict grades, then grades would be the criterion variable. So in addition to my y variable and my x1 variable, I'm going to have a second x variable, which I'll call x2. And that's going to be a grouping variable. And that variable is simply going to be dummy coded with scores of 0 and 1. So it'll be 0 if you're in one group and 1 if you're in the other. So if I have groups that are, say, I have people that are either single or married, I might say if you're married, that'll be group 0. And if you're single, that'll be group 1. Or maybe I have two different cultural groups, and I'll say one cultural group will be called group 0, and the other group will be called group 1. So whatever the two groups are that I'm comparing to see if I have a difference between these two groups, to see if there's a bias or a difference between the groups, one group gets scored 0 and the other gets scored 1. I have a note here that if we can do the same process if we have more than two groups. If we did that, we need to use orthogonal contrast or some other form of multiple contrasts to compare more than two groups. That gets more advanced than what we're going to do in this class, although I have talked about that in other classes. So if you know how to do orthogonal contrasts, you can use that and use the same procedure here and compare more than two groups. For this class, we're just going to focus on comparing just two groups. Finally, I have a note at the bottom of this page that what we're talking about here is actually the same thing as running an analysis of covariance. So anywhere you've ever heard about or talked about or seen or done analysis of covariance, that's actually what we're doing right here. The approach that I'm taking is a regression approach, or it's often called a general linear model approach to running analysis of covariance, where I'm basing it off of this regression formula that you see at the top of the page. But if you were using a software package like, say, SPSS, and you find the menu and go to where it says analysis of covariance, and you say that Y is your outcome, and you say that X2, your grouping variable, is the grouping variable, and you say that X1 is your covariate, and you plug that in, you would get all the exact same results as what we're going to get here in this example where I'm using the regression or the general linear model approach to talking about this. So indeed, what you do, we have our two X variables, our criterion variable Y. I plug that into my regression equation, and I'll get 3 parameter estimates. I'll get the estimate for my intercept, the estimate for slope 1, beta 1, and I'll get the estimate for slope 2, my beta 2. And this slide here goes through what all these things mean. So our intercept is simply the predicted y when all the x's are equal to 0. So in this case, it would be the predicted y when you're in group 0. So maybe that's the married group, might be group 0. And when you're scoring the test score, say that's the social support or the social interaction variable. So when the target test variable is 0, and when you're in group 0, what is your predicted y? That's the intercept. Beta 1 is a predicted increase in a y given a 1 unit increase in your test score. That's basically just your standard beta. And if we want to be technically accurate about what it is, it's actually given us the slope specifically for group 0. It's what is, if you're in group 0, because we can note that the beta gives us the effect of this x when all the other x's are 0. So when x2 is 0, meaning you're in group 0, beta 1 gives you the effect of x1 when x2 is equal to 0. So if we want to be technically accurate, we say when group equals 0. So it's a predicted increase in y given a 1 unit increase in the test score when group equals 0. Now the thing that we really care about is beta 2. This is the thing that's going to pertain to our test bias, because beta 2 says what's the predicted increase in y when you go from group 0 to group 1. So in other words, how much are we under or over predicting for one of these groups? If we are, then we're going to have a non-zero effect for beta 2. So in other words, if we're holding test score constant 0, if everybody has the exact same score on our test variable, so if everyone has the exact same level of social interaction, or if everyone has the exact same level of the GRE score, then what is a predicted increase in y in our criterion given a 1 unit increase in group membership, which is going from group 0 to group 1. And so if this is a non-zero value, it means we have intercept bias. It's just focusing on that. So beta 2, again, it's a predicted increase in y for group 1, holding test score constant. And so if we have a significant effect for beta 2, it's telling us the difference between groups if they had the same test score, which is intercept bias. If beta 2 is significant, we have intercept bias. Okay, now let's talk about slope bias. And to test for slope bias, we're going to use that same equation we just used to test for intercept bias and add one little thing to it. And when we test for slope bias, what we're going to be doing is testing for an interaction. And testing for an interaction is the same thing as testing for moderation. Moderation and interactions are two terms for the exact same thing. And to best understand what moderation is, it is helpful to contrast it with mediation. So I'm going to talk about both mediation and moderation. These are also two very common procedures that are used in research, so it's especially important to understand what mediation and moderation are and what the differences are between them. Although for slope bias is really only going to pertain to moderation. So what is the difference between mediation and moderation? Both mediation and moderation are involving three variables. In both cases, we have an x variable and a y variable, and a third variable, which is either a mediator, if we're talking about a mediating relationship, or it's a moderator, if we're talking about a moderating relationship. So both of these, mediation and moderation, both involve situations where you're looking at three variables. And in both situations, we're going to ask the question about x predicting y. We have an x variable and a y variable, and we want to understand the process of x predicting y. With a mediating relationship, we're going to ask the question of why does x predict y? So, for example, maybe I have a theory that when people have a strong alliance with a medical doctor, they tend to have more positive attitudes towards their treatment plans. And when they have more positive attitudes towards their treatment plans, they engage in better adherence. They're more likely to follow those treatment plans. So according to my model, I'd have an X variable, which is the alliance with a medical doctor. I'd have a mediator, which is the attitude, the positive attitude towards one's treatment plan, and the Y, which is the outcome, which is the person's level of adherence to that treatment plan, how well the person follows a treatment plan. So if we ask the question, does an alliance with a medical doctor predict a person's treatment adherence, our answer is, why, yes, it does. And why does it predict it? It predicts adherence because of attitudes. It predicts adherence because when people have a strong alliance, that leads to more positive attitudes, and those attitudes in turn lead to better adherence. So we're suggesting a pathway, a chain link. And if we took out, if for some reason the alliance didn't lead to more positive attitudes, then it wouldn't lead to better adherence. So we say X leads to M in turn leads to Y. And if we have this sequence, this pathway of X to M to Y, then we're talking about a mediating relationship. In contrast with a moderating relationship, we're going to say, when does X predict Y? Or we're going to ask, when does X predict Y? And the question, does X predict Y, gets answered with the answers that says, it depends. One thing to note, anytime you're talking about a moderating relationship or an interaction, it always means that you're going to answer a question with the word, phrase, it depends. So does X predict Y? Well, it depends on the mediator. So maybe I want to look at how much an alliance with a medical doctor predicts adherence to a treatment plan, but I think that how well the alliance predicts the adherence might depend on whether someone has significant barriers in the way that block them from being able to implement their treatment plan. Maybe they don't live close, and maybe they need to get medication, but they can't afford the medication, or they need to exercise, but they don't have any places they can go to exercise. So maybe in this case, my moderator might be the presence of barriers that hinder one or limit one's ability to engage in a treatment plan. So in this case, we might ask the question, does the alliance predict adherence? Does the alliance with a doctor predict adherence? And the answer is, well, it depends. If there are no barriers, the moderator, if there are no barriers in place, then yes, the alliance does predict the adherence. But if there are barriers, the presence of barriers that make it impossible for someone to adhere to the plan, then it doesn't matter what kind of alliance you have. No matter what, the person can't engage in the adherence and follow the plan. So in this case, the question, does the alliance lead to better adherence? The answer is, it depends. It depends on the presence or absence of barriers. If there are barriers in place, then there's no relationship. It doesn't matter what the alliance is. But in the absence of barriers, then yes, the alliance predicts the adherence, and that would be a moderating relationship. So first, let's talk about how we will test for mediation. So to test for mediation, we will need to run a series of 3 different regression equations. And actually, we could do this by running regression equations, or we could do it in structural equation modeling as another approach. Both approaches will give us the same result either way. I'm going to focus on the regression approach here. But I can depict my 3 equations with the figure at the top of the page. And actually, this is the figure that I would use if I was doing the structural equation modeling approach. First, let's look at the upper right-hand corner where I have I have the circle with X and then an arrow pointing to Y. And that's just simply depicting a regression relationship where I'm using X to predict Y. And I have that equation for that regression relationship right here, where I'm going to say Y hat, the predicted Y, is equal to intercept plus slope times X. And I'm going to name this slope C. So rather than calling this B or beta, I'm going to call it C. And the reason why I'm going to call it C is because that's just the convention. It's typical when people talk about mediation to give names to these slopes of A, B, and C, and there's going to be a C prime. And so I'm going to give labels to different slopes with different letters. and it will follow the convention of how these slopes are typically labeled when people do mediation. So instead of calling this beta B, we're just simply going to label it C, but it's just the beta, it's just the slope. So, and up here, note that I labeled it C right there in my picture as well. So C is going to be the beta if I just use X to predict Y. So that's one regression equation. And then on the left-hand side of the page, I have this triangle-looking figure, and that figure is actually showing us two regression equations. There's two regression equations embedded within that triangle. The first regression equation that's being depicted is saying that X predicts M. And so I'm going to have the equation, this equation I just put the box around, where I say M hat, predicted score on M, is equal to intercept plus a slope times X, and I'm going to label this slope A, which I labeled right here, labeled that A. So the mediator is predicted by X in this equation. So the predicted score on the mediator, predicted M, is equal to slope, so intercept plus a slope, which we call A, times X, which is your score on the predictor variable. And then we have a third equation also embedded within this triangle, is that Y, in this picture right here, Y is predicted by both M and X. So it's a multiple regression equation where I have two predictors. X predicts Y and M predicts Y. So I have two predictors of Y. So I have an equation down here at the bottom saying that Y hat, your predicted score on Y, is equal to an intercept plus a slope, and I'm going to label this slope C prime. I'm going to put that little mark at the top here and call that C prime, plus, and I'll call this, I'm going to label this beta actual with a B, which is that one right there, which will be slope 2 times M. So I've got, this equation has two slopes, the slope for C prime and the slope for beta. And this is just showing you how much if we use both M and X as two predictors of Y, we get what's the effect of M controlling for X and what's the effect of X controlling for M. So these are the equations we will run. And essentially, if I have a mediation hypothesis that I want to test, say I think that treatment alliance is X, say alliance is your X, and that leads to a mediator, which is someone's, say, positive attitude towards treatment, which in turn leads to an outcome, which, say, is adherence to that treatment plan, and that's my mediation pathway. To test that mediation, I need to run all three of these regression equations. So I need to use X, so that would be my alliance, to predict the mediator, that would be attitudes. I need to use X, that alliance, to predict Y, which would be adherence. And I need a third equation where I use both the alliance X and the mediator, attitudes, to predict Y, which would be adherence. So I need to run all three of these equations. So what happens when I run these three equations? What do I get and how do I interpret it? How does this give us information we need? So when we run these three equations, we're going to get three key types of effects that are crucial to understanding mediation. And these are the things that if I was running a mediation analysis, I would probably want to report all three of these different effects. So the first effect I'm going to call the total effect. And we'll call that effect C. And it's this C right here is the total effect of X on Y. So just not considering mediation, to what degree does X predict Y? For example, to what degree does therapeutic alliance lead to adherence? Because if therapeutic alliance doesn't lead to adherence in the first place, then there's nothing there to mediate. So just without the mediator, to what degree does X predict Y? To what degree is there something there to mediate in the first place? And we're going to call that the total effect. And then we're going to break that total effect into two different parts. One part will be the direct effect, and the other part will be the mediated effect. And if I have a mediating hypothesis that there is a mediating effect, then the mediated effect is the one I'm most interested in. So the direct effect is to what degree is the same thing as a non-mediated effect. So to what degree does X predict Y have a direct effect after controlling for the mediator? So this would be stuff that X explains in Y over and above the mediator. So it's stuff that's not mediated at all, but X having a direct effect on Y that's not mediated, but just directly predicting Y regardless of the mediator. So this might be if alliance predicts adherence over and above what can be understood by someone's attitudes. So if alliance, and this would be if we find that after controlling for someone's positive attitude, if alliance still predicts adherence after controlling for my mediator, that would be the direct effect. It would be a non-mediated effect. The effect of X on Y after controlling for the mediator. In contrast, the mediated effect is a pathway through the mediator. To what degree does X lead to the mediator, which in turn leads to Y? So for example, to what degree does alliance lead to attitudes, which in turn lead to adherence? That's the key pathway we're looking at that we want to understand if we have a hypothesis about a mediated effect. And we can calculate that effect as simply A times B. So if we run a regression equation and get the beta for A, if we use X to predict M, and we run another regression equation where we use M and X to predict Y, and we get the beta weight for M predicting Y after controlling for X, we have these two coefficients. We have the beta weight A and beta weight B, and I simply multiply those two together. A times B, the product of those two beta weights will actually give me the mediated effect. And as it turns out, that will be mathematically equivalent to taking my direct effect, C, minus C prime, the direct effect. So total effect minus direct effect gives us the mediated effect, and also pathway A times pathway B, the product of my two mediation pathways, gives me that exact same mediated effect. And so when we run this type of analysis, we can ask a question of how much of the effect on X on Y, assuming there is an effect. We want to start by looking at that total effect, because we don't have anything there to begin with and there's nothing to mediate. But assuming we have a total effect, then we can ask the question, how much of that total effect is mediated through our mediator, and how much of that total effect just has a direct effect on Y after controlling for our mediator over and above what can be explained by the mediator. And if we run an analysis and we find that that everything is explained by the mediator, that mediating pathway explains everything, and that this C prime becomes non-significant or very, 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 very small, that essentially that's so small we can get rid of that and say everything goes by this pathway there, then I would call that full mediation. In contrast, and which is probably much more common, is to have a situation where we have partial mediation. Some of the effect goes through that pathway, but we still have maybe a significant direct effect over and above that mediated effect. And if that happens, I would call that partial mediation. One thing to note whenever we're testing for mediation is that mediation does not test causal relationships. It can't tell you, does one variable actually lead to another in a temporal order. It doesn't say, does one variable actually cause another? Just like anytime we're running correlation or regression, we make assumptions about how we theoretically think the variables should be related. But a regression equation cannot tell us that this variable actually precedes or predicts temporally in terms of time. It doesn't actually confirm that. So the causal pathways in our model are assumptions, but not things we're actually testing. So we're saying if we've arranged it according to if our assumptions are correct, if this one really comes first and that one really comes second, what degree do we have a mediating pathway there? But just a significant results from a mediation model does not necessarily mean that we've arranged our variables in the correct sequence. So that's something to keep in mind, that we're testing, we're assuming we have the correct sequence, but we're not actually testing whether that sequence is specified correctly or not. Just as any time we're running correlation or regression, we might have assumptions about the order of the variables or the causal effects, but we're not actually testing causal relationships. Okay, at this point, we've talked about how we calculate our mediated effects, our total effect, our direct effect, and our mediated effect, but we haven't talked about how we would calculate significance or determine if our effects are significant or not. Now, for the total effect and direct effect, it's fairly straightforward. We have our effect C, which we use X to predict Y in a simple regression equation, and we get a beta weight, and if that beta weight's significant, then it means our total effect is significant. And so that's just the significance of that simple regression equation. Likewise, our direct effect, we have a regression equation where we use both our mediator and X to predict Y. We have two predictors of Y, and we get this C prime is the effect of X on Y after controlling for M. That's our direct effect. And if that beta weight for C prime, if that effect of X on Y after controlling for M, if that's significant, then we have a significant direct effect. So we can get a beta weight for C, and if that's significant, we have a significant total effect. We can get the beta weight for C prime, and if that's significant, we have a significant direct effect. But what about this mediated effect? How do we determine if that is significant? And that's the thing that suddenly makes mediation a rather complex analysis, because there's not really a good way, there's not an easy way to do this. For most beta weights, recall that we test significance of a beta weight with a t-test. We take a statistic divided by its standard error, and we will have a t-test. And so a beta divided by its standard error will give us a t-test for a beta, and a t-test has a known distribution if the null hypothesis is true, and it allows us to determine the probability of our effect under the assumption the null hypothesis is true. But and there's some formulas out there for calculating a standard error of a mediated effect, but they don't work exactly right, and they don't give us distributions that exactly follow a t-distribution. And so there's not a particularly easy way, there's not to go about determining if your mediated effect is significant. So what are we going to do? The current approach that everyone uses, that's the current recommended approach for testing significance of a mediated effect. And note that this is the point we've run our analysis. We know what our effect is. We calculated pathway A, we calculated pathway B, we take the product of the two, we have our mediated effect. So we know what it is. We just don't know if it's significant or not. And so to test significance, we can't really use a t-test, although, well, there's some formulas that they try to do that. They don't work all that well. But a better approach is to do this thing. Bootstrapping. I'm going to test the significance of the mediated effect using something called bootstrapping. I think the term bootstrapping comes from the phrase pulling yourself up by your own bootstraps. And as you will see here, what we're going to do is to create a simulated population by pulling ourselves up with our own sample. So what we do is we assume that our sample is a model of the population, and we're going to create a simulated population based on our sample. So if I did a study and I was testing a hypothesis that attitudes mediate the effect between, say, alliance and adherence, and say I got a sample of 100 people. And so in the study, I would have everyone's scores on their alliance with their medical doctors. I would have everyone's scores on their attitudes, their positive attitudes towards their treatment plans. And I would have assessed everyone's level of adherence to their treatment plan. So I'd have 3 scores for every single person in my sample, scores on X and M and Y. And And then I'm going to assume that my sample is a model of the population so that I can just simply copy and paste my sample and make duplicates of my sample and paste them and add them together. So I take, my sample of 100, copy and paste it. Now I've got a sample of 200, and then copy and paste that. And now I've got a sample of 400. So I'll just copy my sample over and over and over again and tell the computer to make a population that's what we would get if I simply made an infinite number of copies of my sample. So now I have this huge infinite simulated population based on my sample. And then I'll tell the computer, once you have the simulated population, to sample from this population what I'll call a bootstrap sample that has the exact same sample size as my original study that I conducted. So if I originally did a study with 100 people in it, I will tell the computer to collect or draw from that population sample with 100 cases, so that n equals n. The sample of the bootstrap sample should be the same sample size as the sample that I actually tested in my original study. So once the computer has drawn this bootstrap sample of 100 cases, the computer can then calculate that mediated pathway using the simulated bootstrap sample. And then once the computer has calculated that mediated effect using the simulated sample, I will tell the computer to repeat. Do this over and over. We usually need to pick a number. A common number to pick is, say, 1,000. So we'll tell the computer to do this 1,000 times to create 1,000 bootstrap samples, and for each bootstrap sample to calculate the mediated effect for that sample, and to calculate that A-B pathway. And so the computer will, we have our simulated population. It will draw a sample of, say, 100 people from that population and calculate the mediated effect. Then it'll draw another sample and calculate the mediated effect for that sample. And then it will draw another sample and calculate the mediated effect for that sample. And it will do it over and over and over again. And maybe I tell it to do it 1,000 times. Now, think about what we're simulating in this process. Think about that googly-eyed sheep table and the different types of distributions that we deal with. What type of distribution are we simulating here? We're simulating a distribution of sampling error. Recall that when we talk about distributions, one way to talk about them is to think about the two questions: observations of what, deviations around what. And sampling error, the answers to those questions are observations of what? Well, it's observations of statistics from different studies that we do over and over again, replications that we do over and over again. Deviations around what? It's deviations around the true population parameter. So in this case, we're assuming that our sample is a model of the population, and from that we've created this simulated population, and we're replicating our study. We're drawing from that population a sample and calculating our statistic, and then we draw another sample, calculate our statistic, and we're replicating our study over and over and over again. And that's creating a distribution of sampling error. And we can use the abbreviation for the typical size of our sampling error, which is the standard error of our statistic, with the SD subscript name of statistic. So anytime I have SD, and then I have a subscript that has, I'll just write down here, name, N-A-M-E, for name of statistic. So if I have SD, and the subscript is a name of a statistic, then that is a symbol for the standard error of that statistic. So if it's SD subscript mean, it's the standard error of the mean. It tells me if I replicate my study over and over again, each time I calculate a mean, draw a sample, calculate a mean, draw a sample, calculate the mean, how much does my mean typically deviate from the true population parameter? That would be the standard error of the mean. Or if it's SD subscript beta, that would be the standard error of a beta weight. That is, if I do my study, calculate a beta, replicate my study, calculate the beta, do that an infinite number of times, and how much does my beta from all my replications typically deviate from the true population parameter? That would be the standard error of the beta. In this case, we're looking at the standard error of the mediated pathway. That is, if we have our simulated population, we draw from that population, calculate the mediated effect, and then we replicate that over and over again. The distribution of all those different mediated effects from all of our different replications is the distribution of sampling error. And the SD of the mediated effect is the standard error of the mediated effect, which is the typical size of the error that we make when we replicate our study over and over again. Now, because this distribution is not going to fit a known distribution shape, instead of we can't really do like a t-test. There are some formulas that try to simulate that, but they don't work all that well. So we have an issue here that we can have a distribution of sampling error. We can have a standard error of our mediated effect, but it's not something that's going to fit a mathematically defined shape like a t-distribution. So what we're going to do is we're going to take all of those bootstrapped values that we created. So if we replicated our study 1,000 times in this example, we'll have 1,000 different mediated effects from 1,000 different bootstrap samples. And we're just going to line all those mediated effects up in ascending order from high to low. And from that, we're going to define a 95% confidence interval. So we can identify the values that fall at the bottom towards a 2.5%. How do you say that? 2.5%, about the third percentile, between 2 and 2.5th percentile, and the 97.5th percentile, however you say that, to identify what is the range of scores where 95% of the cases fall, which, by the way, I think there might be some notes where that's misstated, the 5th and 95th percentile, but to make this a 95% confidence interval, it needs to be 2.5 and 97.5. So we'll identify that range, which 95% of those mediated effects fall. And then simply we can look at that range and see, does that range include a 0? And if that range includes a 0, then we can say our results are not significant. And if the range excludes 0, if there's no 0 in that range, so if we calculate a bunch of mediated effects and say in our study we got a mediated effect of 0.6, and if we calculate this interval, we find that at the 22.5th percentile, maybe it's an effect of 0.2, and the 97.5th percentile maybe was a 0.9. Well, from 0.2 to 0.9, that doesn't include 0, so we would say the mediated effect is significant. In contrast, if we found that at the 2.5th percentile, the score was maybe a negative 0.3, and the 97.5th percentile, the score was, say, a positive 0.8 or something like that, well, that range does include 0, so we would say the result is not significant. So that is how we would test the significance of a mediated effect with bootstrapping. So now let's talk about moderating relationships. How do we test for moderating relationships? Recall that to test a moderating effect, we have an x variable predicting a y variable, and we're asking the question, does x predict y? And the answer is going to be, well, it depends. We want to see if the relationship between x and y depends on a third variable, whether that relationship might be strong for one group and weak for another group. Here's an example I have where I have this idea for frogs, that maybe if I have a test called the Frog Dancing Skills Test, or FDST, the Frog Dancing Skills Test, and I want to see if frog dancing skills might predict how well frogs acquire mates. And in this example, I have this idea that maybe it might depend on what cultural group the frog is from, that maybe there's different frog cultural groups, maybe. And maybe some frogs can come from a cultural group that uses dance. That's part of their tradition of how they acquire mates. And maybe there's another cultural group that doesn't use dance to acquire mates. And so, what I'm looking at here is whether frog dancing skills predicts acquiring mates, and whether it might be moderated by, that is, if there's an interaction, if it might be moderated by whether the frog's cultural group. So the cultural group could be the moderator, with the idea that culture might moderate the relationship between dancing skills and acquiring mates. In other words, the idea is that if the frog comes from a culture that uses dance, then dancing skills would be a strong predictor of acquiring mates. And if the frog does not come from a culture that uses dance, then dancing skills would not predict acquiring mates. There would be a lack of a relationship for one culture and a strong relationship for another culture. In this example, I'm going to be looking at situations where our moderator is a dichotomous grouping variable where I have members of one group or another group. So in this case, we'll look at, is a frog a member of the dance culture or the non-dance culture? I have a note at the bottom of the page here. Keep in mind that we could actually have a numerically scaled moderator as well. So it doesn't actually have to be a grouping variable. Everything I'm going to be talking about here could be applied to a situation where we have numerically scaled variables that range from high to low that aren't simply dichotomous grouping variables. So we can do this with a dichotomous group or with a variable that's, maybe I could have a variable that's to what extent does the frog culture like dance? So we could have maybe some have come from a high dancing culture and medium and low and moderate and everywhere in between. So maybe how much your culture values dance could be a numerically scaled variable that ranges from high to low, and that would work for this same model as well. But for this example, we're going to focus on situations where our moderator is dichotomous, two groups. Okay, so we're going to test for moderation using, yet again, another regression equation. But before we do this regression equation, we're going to need to transform our variables just a bit. So sometimes we've done regression analysis and we've converted everything to z-scores prior to analysis, and we can have regular betas and standardized betas. For testing for interactions or testing for moderation, these transformations are very important. And if you don't do them right, you're going to come with results that don't make sense. So we do need to take our x variable, which is, we'll call that our score on our test. So if maybe this is my frog dancing skills test, the target test that maybe I want to validate, or I want to see if the results of this test are moderated by a third variable. So I'll have my x variable as a score on the test, and it's important, I do need to convert that to a z-score. So x needs to be changed to a z-score with a mean of 0, standard deviation of 1. Then for my moderator variable, this is going to be group membership. And if we're testing for slope bias, usually we are dealing with a dichotomous, we have two groups and we have a dichotomous variable, and we want to see if we have a stronger slope in one group and a weaker slope in another group. And so we're going to focus on that type of dichotomous comparison here. And we need to arbitrarily pick one group to be kind of like the target group so that we can score it so that you'll get a score of 1 if you're a member of a target group, and 0 means you're not a member of that group. So maybe we'll score it so 1 is you're a member of the dancing group, and 0 means you're not a member of the frog dancing group. Is one way we could do that. So we've created a moderator variable. We've done the same way we've done before. We had a grouping variable where we have zeros and ones to determine group membership for the variable. So it's the same thing we just did just a moment ago when I was talking about intercept and slope bias. I have a note here that we're going to focus on dichotomous variables for this class. If you were dealing with a numerically scaled moderator that ranged from high to low, then I'd say don't do zeros and ones. Instead, for that, I would convert it to a z-score. But we're not doing that in this class. That's just a note for your own reference, that if it wasn't dichotomous, I would convert it to a z-score. So we've got, at this point, two key variables. We've got our target scale, say that it's the Froggy Skills dancing test, and we converted that to a z-score, and then we have our moderator variable, which is your group membership, scored either 0 or 1, depending on what group you're in. And then we have our outcome variable, y, say maybe it's how many mates the frog acquires. And at this point, this is actually not essential. The first two transformations I mentioned of the x variable needs to be z-score. That's essential. But the y variable, it's recommended, but not essential. But I just always do this. It makes results so much easier to interpret. So I always convert my y variable to a z-score as well. So I have here, it's not required, but it will make results much easier to interpret. So now I have my x variable is a z-score. My grouping variable is either zeros or ones. And my y variable is also a z-score. Now, here is the key thing that involves interaction or testing for moderation. Whenever we're testing for moderation, whenever we're testing for interaction, those are, again, the same thing, it always involves creating a term that's created by multiplication. So I'm going to multiply two scores together to get what I will call an interaction term. So I'm going to create this thing called an interaction term. So at this point, I have scores on X and Y and the grouping variable, and I'm going to create yet another variable, which I will call my interaction term, and I'm going to create this variable by multiplying together my two predictor scores. So in this case, I have an X variable and a moderator variable, and I'm going to simply multiply them together. So if my X variable was the Froggy Skills dancing test, and moderator is a group membership, zeros and ones, whether or not you're a member of the dancing culture or not, I'll take your score for the group membership variable and multiply it by your score for the Froggy Dancing Skills test, for the X variable. And I'm going to call that new variable, that product that I get when I multiply those two scores together, that product will be called the interaction variable. And whenever we test for moderation, whenever we test for interactions, it always involves some kind of analysis where we're creating an interaction term produced by multiplication. That's always how we get an interaction term. And if you say moderation, if you say interactions, what it means is you've created this interaction term through multiplication. So let's consider, why did we do this? What do we accomplish by creating this interaction term? Why is that useful or valuable for us? What do we learn from that? So I have another question. What will happen if an interaction variable is used as a predictor in a regression equation? So let's look at that and see what we get by creating this interaction term. So here's an example. Say I have, I have a sample of 5 different frogs here. And this first column gives their score on the Froggy Dancing Skills test. And I've converted all these to z-scores, I believe. So this frog, the top frog, did rather poorly, got a negative 1.36 over a standard deviation below the mean. This next frog did a little bit above 0.47. This third frog also a little above the mean, 0.21. Next frog, this one did kind of poorly. This frog down at the bottom, that frog did wonderful. That frog got a score of 1.25, very high dancing score. So we got each frog's dancing score here. Now we got that second variable. Recall, by the way, this first one, the Froggy Dancing Skills test, that's variable X. And then the member of dance group, that's variable M. That's our moderator. And it scored either ones or zeros. So these first 3 frogs are all members of the dancing culture group. And these last 2 frogs are not members of that group. They're members of the non-dancing culture. And so everyone in the dancing culture gets a score of 1, and everyone in that non-dancing culture gets a score of 0. Now let's see what happens when we create our interaction term. We create our interaction term by taking your score on X and multiplying it by the moderator. So negative 1.36 times 1 gives us negative 1.36. 0.47 times 1 gives us 0.47. 0.21 times 1 gives us 0.21. And then for the people in group 0, they're just going to get a bunch of zeros because everything times 0 equals 0. So negative 0.57 times 0 gives us 0. And 1.25 times 0 gives us 0. So we've essentially created this interaction variable that's saying if you're in group 1, your predicted score here, this variable we're going to use as a predictor, is your score on the Froggy Dancing Skills test. And if these are all z-scores and 0 is the mean, we're saying if you're in group 0, your predicted score is simply the group mean. In other words, we're saying if you're in group 1, your score is relevant, and we're going to enter that in the equation. But if you're in group 0, your dancing score is irrelevant, and so we'll just give you zeros, which is z-scores. So these are group means. We're just going to give the predicted group mean for everyone, assuming that dance is irrelevant. So we've created this variable that's essentially modeling a hypothesis that the dancing score is going to be relevant for people in group 1, and it's going to be irrelevant for people in group 0. And now we're going to do a regression equation where we put all 3 of these variables, X, Froggy Dancing Skills test, moderator, and the interaction term, all 3 of those things are going to be put together in the same regression equation. So here's what our equation will look like. So this is a regression equation testing for an interaction. Now, one thing to keep in mind is that whenever you test for a moderating relationship, that is, whenever you test for an interaction, you have to create this interaction term by multiplying two variables together. And when you create an interaction term, you always need to include the original two variables that were used to create that interaction term. Those two variables need to be included in your equation. I would never test in a regression equation an interaction term without what I'll call the main effects for the two variables you used to create that interaction term. So I have up the top here, the variables used to create the interaction term always need to be included in the equation along with the interaction term. If you don't do that, you're going to get meaningless results. You'll get weird stuff. You might get stuff that makes it look like there's an interaction when there's not. So in my example here, y was the number of mates that a frog got. And so predicted y hat, that's the predicted score for how many mates the frog got. x1, that's my target variable, which is the froggy dancing skills test. That's the test I want to validate. And so everyone has a score for x1. And then the moderating variable is the dance group membership, either a 0 or a 1. And that goes there. And then I've created this interaction term. Everyone's score on x1 times their score on the moderator, created an interaction, and I put that interaction right there. So now I have a multiple regression equation with three predictors. The outcome variable is the score on the number of mates, and I'm predicting number of mates with froggy dancing skills test, x1, and group membership, moderator, dance group membership, and the interaction term. X interaction term is the product of x1 and the moderator. So when we create this equation and we plug it in and we get estimates for our parameters, what do we get? We'll get results that will give us an intercept, and it'll give us three slopes: the slope for x1, the slope for x2, and the slope for x3. What do those parameter estimates tell us? So first, our intercept, and some of this is going to be very similar if we went back to when I was talking about intercept bias. This is going to be very similar to the equation for intercept bias. In this case, our intercept in this equation, beta naught, gives us the intercept for group 0. And I forgot, who was group 0? What did I say? Group 0 was the group that non-dancing. So this would be the intercept for the non-dancing group. And here's our slope for the non-dancing group. So beta 1 is going to be the slope for group 0, because again, these will be the slope when all the other x variables are 0. And so if I have a group variable that's 0s and 1s, it's going to be the slope for group 0. And then beta 2 is the change in intercept for group 1. This is exactly what we saw in our previous example for intercept bias. So if beta 2 is significant, that means we have intercept bias. So note that essentially these first three components are the same things that we had when we were looking at intercept bias. And what I've added is this third thing, which is a slope for our interaction term. And one way to think about this is that we have an intercept for group 0, and then beta 2 tells us how much the intercept changes for group 1. Then we also have a slope for group 0, and beta 3 tells us how much that slope changes for group 1. So beta 2 is giving us information about intercept bias, and beta 3 is giving us information about slope bias. And if beta 3 is significant, it means we have slope bias. Now, if you have standardized y, as I recommended doing, we can be more specific about exactly what these scores are. So if y is also standardized, then our intercept is actually the intercept for group 0 as a z-score. So if it's negative, it means they're below the mean for your entire sample. If it's positive, it means they're above the sample mean. So it's a z-score mean. It's a z-score, the mean for the group 0 in a z-score format. Beta 1 then becomes the standardized beta for group 0 because everything's now standardized. beta 2, this is our test for intercept bias, the difference between the two groups' predicted scores if they have the same score on the predictor variable. So this would be the extent to which there's differences between the frogs in the dance culture and the non-dance culture if they had the same exact score on the dance skills test. And if Y is turned into a Z-score and X is scored as zeros and ones, then beta 2 is going to give us the size of difference between two groups in standard deviation units. In other words, it will essentially give us the D statistic, because it'll be interpreted as a size of difference between the two groups, and Y has been converted to a Z-score, so it'll give us a difference between two groups in standard deviation units. So essentially, beta 2 becomes a D statistic. And then beta 3 is the change in the standardized beta for group 1. So the key thing is, if you turn Y into a Z-score and you followed all the other specifications I gave you for how to convert the scores, our betas become standardized betas, beta 1 and beta 3 become standardized betas, and beta 2, the one testing for intercept bias, gives us the size of the difference between two groups in standard deviation units, which is essentially a D statistic. And I have a note down at the bottom here that note that my format here, let me back up to the previous slide, when I talked about how to score things, that we've got the moderator is ones and zeros, so that is not a Z-score. And the interaction term, when you create this interaction term, this is not going to be a Z-score either. So what that means is if you run an analysis, say in SPSS, and you get automatic standardized output, in this case, the standardized output is not really easy to interpret. You don't want to look at that. You want to, for testing for an interaction, you'd want to score your variables ahead of time like I specified, and then we can interpret the results and they will be meaningful. And I would not use standardized output from a software package for this type of analysis, because this gives us something slightly different. It will standardize your interactions and it will standardize the group comparison, and that kind of messes everything up. So once we have run our analysis, let me back up to the previous slide. Once we've run our analysis and we've got our effects here, and say we have an interaction and that's significant. So if we have a significant interaction, it means we have a significant interaction effect. And so if we ask the question, say, does froggy dancing skills predict mate acquisition? The answer is, it depends. It depends on the moderator. That the strength of relationship between X and Y depends on the moderator. If the moderator's one value, it's a strong relationship. And if the moderator's a different value, it's a weak relationship. But exactly how does this go? Is it that the people in the dancing culture have a stronger effect, and the people in the non-dancing culture have a weaker effect, as we might predict, or is it the reverse? And exactly what is this difference? Exactly how is it that it depends on the moderator? So at this point, we've just determined that we have an interaction. We've determined that we have a moderating effect. That is, if our beta 3 is significant, that means we have a significant interaction effect. But we need to do a little bit more to understand what is happening with the interaction. So we need to do something. I'm going to say we need to probe our interaction. We need to understand what exactly is going on. And one good way to do that is to do something that we'll call calculating simple effects. Another term for this is to call these conditional effects. And what we want to do is say, what are the effects? That is, what is the slope, or actually really want to know, what is the intercept and the slope for people in one group, and what is the intercept and slope for people in another group? Because if we have a significant interaction, it's saying that our slopes are not the same for the two groups. So what we want to know is, what is the slope for group 1, and what is the slope for group 0? And we'll call these simple effects. And as we're doing this, we'll get both the intercepts for both groups and the slopes for both groups. So we'll get the simple or conditional intercept for group 0 and group 1, and the simple or conditional slope for group 0 and 1. And that way we can tell which group has a stronger slope and which group has a weaker slope, and exactly what is the slope, what is the effect of the dancing skills in predicting mate acquisition, how strong is that relationship for the frogs in the dancing culture group, and how strong is that relationship for the frogs in the other cultural group. So in my example, I'm going to focus on a situation where we have a dichotomous moderator variable. That's what we've been looking at, where I have two groups, group 0 and group 1. So that's what we're going to be looking at. What are the target levels? That is, for group 0 and group 1? That is, what's our intercept and slope for group 1? What's our intercept and slope for group 0? We could, if we had a numerically scaled moderator, we could pick two values. Like we could say, what's the intercept and slope for people who are one standard deviation above the mean? What's the intercept and slope for people who are one standard deviation below the mean? So we could just pick two values on our moderator if our moderator was numerically scaled. So in our example here, we've got a moderator that's just two groups, and it's fairly obvious what two values we want to pick. We want to pick 1 for people in group 1 and a 0 for people in group 0. Those are the 2 points we want to pick, group 1 and group 0. If we had a numerically scaled variable that ranged from high to low, it would be a little more arbitrary. We'd have more of a question about what two levels do we want to pick. And a common thing to do is to do this. We just look at one standard deviation above the mean and one standard deviation below the mean are your two levels that you pick. Okay, but we're going to focus on a dichotomous situation where I have two groups, people in group 1 and group 0. So to calculate simple effects, what I'm going to do is I'm going to rearrange the terms in my regression equation. And if you want to, you can look at this and look at the basic algebra here. I've just rearranged. So here I have my regression equation, and this is the same equation. Let me just go back right here at the top of this page here. Here's our regression equation written out how we used to see it. So the top of the page there is the usual way for writing a regression equation. And what I've done now on this page is I've just rearranged the terms of that exact same equation. So this is the same exact equation. I've just rearranged the terms around. And when I rearrange the terms this way, what I have is this part here is going to be something that will give me a value for the simple intercept for each group. And this part here will answer the question about what is the slope for each group. And so what I can do once I've rearranged the terms this way is that notice within each box, the only x variable is the x variable for the moderator. So here I've got x, here's the x for moderator, then over here on my right box I've got x moderator. So I've got two boxes, and in each box I've got a moderator, then the x1, which is say it's the froggy dancing skills test, it's my test variable, that one's outside of the boxes in the way I've arranged this. So if I run a regression model and I get all the beta weights, I get an intercept and slope 1, slope 2, slope 3, so I've got my 3 beta weights, I've got my intercept because I ran my regression model. And say I ran my model, my intercept was, and my interaction term was significant, so I want to calculate some simple effects. I want to probe my interaction and figure out exactly what's going on. So at this point, I have the beta weights from a model. And so I could substitute these betas here, and I could actually put in the actual beta weights that I got when I ran my equation. So all these beta weights, and let's assume I did that. Let's assume I ran my model, I got my beta weights, and I put the actual beta weights in for my model. And then I wanted to pick two desired values from a moderator. And if I have a dichotomous group situation, like I was saying, I'm just going to have group 1 and group 0. Those are going to be the two levels of my moderator, a 1 and a 0. So I can say, what does this box become if the moderator is, if you're in group 1? And I have the beta weights from the equation I just ran, so I can take the intercept plus beta 2 times 1, and that would actually give me the intercept for people in group 1. And then if I take my intercept plus beta 2 times 0, that would give me the intercept for people in group 0. So what I'm doing here is I'm taking the beta weights, the intercepts and the slopes from my from the equation I just ran, and I plug those into my equation here. And then I take target values for my moderator, and I picked like two values. So I could say if the moderator is 1, let's put that right here. If moderator is 1, then that will be 1 right here. And then I can calculate what is the intercept plus slope 2 times 1. And that gives me what I'll call the simple intercept. The simple effect is the intercept for people in group 1. And then I could do the exact same thing for people in group 0. I'll put a 0 right here. Intercept plus beta 2 times 0, which that actually makes, if you think about it, that actually makes sense because beta 2 times 0, that's going to become 0, that'll drop out, and that just becomes intercept. And recall, I already said that your beta 0, your intercept, is the intercept for people in group 0. So that is, that makes consistent with what I already said. So that is your simple intercept for people in group 0. And we can do the same thing for the slope over here. So I ran my equation. I have the value for beta 1. I have the value for beta 3. And then I can say, well, what if someone's in group 1? If the moderator, if xm, if the moderator is equal to 1, I'll put that here, beta 1 plus beta 3 times 1, that will give me the slope for people in group 1. And we can do, likewise, we can, what if someone's in group 0? Put a 0. I'll take our beta 1 plus beta 3 times 0, and that will give me the slope for people in group 0. And of course, if you're in group 0, beta 3 times 0, that just drops out, becomes 0, and it simplifies simply to beta 1, which if you review back, that's actually what I said a while ago, is that beta 1 actually is the slope for people in group 0, and we've just shown it again here. So this way, we can get the intercept and the slope for people in group 1, and the intercept and the slope for people in group 0, and then we can compare them and see which slope is stronger and which one is weaker. And that's a way to probe your interaction term. So just to summarize, at the top I have the regression equation in its original form, and we can calculate these simple effects for a dichotomous meter scored as 0 and 1 in the following way. So group 0, it simply becomes whatever beta 0 is, whatever beta naught, whatever your original intercept is. That intercept already is the intercept for group 0. And beta 1, this already is the slope for group 0. Oops. And intercept plus beta 2, right down here, intercept plus beta 2, that becomes the intercept for group 1, for the second group, or group 1, and beta 1 plus beta 3, down here, beta 1 plus beta 3, that becomes the slope for group 1. So that way, we've got a simple intercept for group 0, a simple intercept for group 1, and a simple slope for group 0, and a simple slope for group 1. So that is how we probe the interaction to determine what it means. If we just find a significant interaction, that in of itself doesn't tell us exactly what's going on. By calculating these simple effects, we will clarify exactly which group has the stronger slope and which group has the weaker slope, and exactly what is the slope for each group. Just one thing to note again, and this is actually, I already mentioned this before, is that when you run these analyses, you do not want to get the fully standardized output from a computer software program, because xm, that's our moderating variable, we scored that zeros and ones, that should not be z-scores. Our interaction term, that should be a product of two variables, that should not be turned into a z-score. And if you were to standardize everything, that would mess things up. So this format here for probing an interaction, it'll become all messed up. It would not work. It would not give you accurate results if you had a standardized, fully standardized output, like if you ran SPSS and looked at the standardized betas, that's not what you want. You need to make your transformations before you do your analysis, and don't use a standardized output from a software package for this particular approach. One final thing, and this is just for your reference, but once we have calculated those simple effects, we can test each simple effect to determine if by itself it is significant. And this slide is just giving you the formula you could use to calculate that, do a significance test. It actually gives you the formula for the standard error of theta, and theta is just another term for that simple effect. And then if you take the simple effect divided by the standard error, you would have a t-test, and you could determine the significance that way. But the formula is rather complex, and I don't want to take time going over that. But just know that you can test the significance of your conditional effects, of your simple effects. And this is if you need it for your reference here, that's the formula you can use to determine your standard errors that could then be plugged into a t-test. So just a summary of how we would go about testing for an interaction. We need to transform our variables. We need to our target X variable needs to be a z-score. Our moderator needs to be scored 0s and 1s if it's dichotomous. Then we need to create an interaction term by multiplying our z-score target variable times our 0, 1 moderator variable. And then we calculate a regression equation. And then we look and see, is that interaction term significant? If it's not significant, there's no point to going any further and probing the interaction. But if the interaction term is significant, then we can go and probe that interaction and calculate our simple slopes for each group to see which group has a steeper slope and which group has a weaker slope, and exactly what the slopes are for each group. And then we can also test those slopes for significance as well. And that is the end of Unit 9.